The tube felt impossibly light in my hands. 13 pounds, 4 ounces. I had lifted ammunition boxes that weighed more. It was the morning of March 6th, 1945, and I stood at the Sagami Proving Grounds 30 miles southwest of Tokyo, holding an American weapon that would destroy everything I believed about physics and engineering and the war we were losing. My name is Tanaka Hiroshi. I was 29 years old, a weapons engineer with the Imperial Japanese Army's Technical Research Institute, and I had graduated top of my class from Tokyo Imperial University with highest honors in mechanical engineering. I had designed improvements to our Type 38 rifle. I had consulted on our anti-tank weapons development. I understood metallurgy, ballistics, and explosive chemistry, or so I thought. The device in my hands, this crude metal tube the Americans called a bazooka, after some comedian's musical instrument, was about to teach me that everything I knew was wrong. 100 meters away sat a Type 97 Chiha medium tank, decommissioned but intact, its armor plating still hard, still 1 inch of solid steel at the front, still capable of stopping any rifle round or machine gun bullet we possessed. Next to the tank, arranged on wooden stands, were test plates of varying thicknesses. 2 inches, 3 inches, 4 inches, 5 inches, and finally 6 inches of hardened steel plate. We had prepared these plates because intelligence reports we had dismissed as exaggerated, as panicked battlefield observations from dying men claimed this simple American tube could penetrate armor that would stop anything except our heaviest anti-tank guns. I did not believe it. I could not believe it. The physics did not allow for it. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. To understand why the moment that followed shattered my world, you must understand what I believed in March of 1945, and why I believed it with the certainty of proven science. I was born in 1916 in Osaka, the third son of a textile merchant who had prospered during Japan's rapid industrialization. My father wanted me to join the family business, but I had different ambitions. I excelled at mathematics and science in school. My teachers told me I had a gift for understanding how things worked, how forces interacted, how materials behaved under stress. When I earned admission to Tokyo Imperial University in 1934, my father finally accepted that I would not be measuring silk but calculating tensile strength and explosive pressures. The Japan I grew up in was a nation transformed. We had defeated the Russian Empire in 1905, a victory that sent shockwaves through the Western world. An Asian power had destroyed a European empire's fleet, had captured Port Arthur, and had forced the Tsar to negotiate peace. We had proven that Japanese soldiers, Japanese sailors, Japanese engineers could match and exceed anything the white races produced. This was not propaganda. This was a documented historical fact. The battleship Mikasa, the rifles our infantry carried, the artillery that pounded Russian positions, these were real weapons, proven in battle, acknowledged even by our enemies as formidable. When I entered university in 1934, Japan had already seized Manchuria, had withdrawn from the League of Nations, and had begun the construction of an empire that would liberate Asia from Western colonialism. This was the narrative we learned, and it was supported by evidence we could see. Our Zero fighter aircraft dominated the skies in the early years of the Pacific War. Our long-lance torpedoes could strike from ranges that British and American torpedoes could not match. Our soldiers had conquered Singapore, the supposedly impregnable British fortress, in 70 days. These were not myths. These were verified achievements. I graduated in 1938 and immediately joined the Technical Research Institute. The empire needed engineers, needed innovators who could arm our soldiers with weapons that would secure our conquests. I was assigned to the Anti-Armor Weapons Division, and the problem seemed straightforward to my 22-year-old mind, drunk on academic success and national confidence. Tank armor was steel-hardened, thick, but still just steel. To penetrate steel, you needed projectiles of greater hardness traveling at high velocity, or you needed large explosive charges placed directly against the armor. These were the two established pathways in anti-tank warfare: kinetic penetration through velocity and mass, or contact demolition through explosive force. Every weapons engineer in the world understood this. It was settled science, as fundamental as Newton's laws of motion. We developed the Type 97 20mm anti-tank rifle. It weighed 59 pounds, required a two-man crew to operate effectively, and could penetrate 30 millimeters of armor, roughly 1¼ inches at 100 meters range. Against the light tanks we encountered in China, it proved adequate. Chinese forces had mostly obsolete armor, thin-plated vehicles that our rifle could defeat. But we knew the Americans and British were building heavier tanks, so we designed the Type 4 70mm rocket launcher. It was cumbersome, difficult to aim, prone to rocket tumbling in flight, but it represented our best effort at a man-portable anti-tank system. The doctrine I learned, the doctrine taught at every military engineering school in Japan and Germany and even America, was clear. Armor protection increased with thickness, and anti-armor capability increased with projectile velocity and mass. This created an arms race. Thicker armor required more powerful guns, which required heavier tanks, which required stronger engines. It was an evolutionary process with clear physical limits. You could not make armor infinitely thick without making the vehicle immobile. You could not make guns infinitely powerful without making them too heavy to transport. This balance defined armored warfare, and within this framework, Japan's position seemed defensible if not ideal. Yes, American tanks had thicker armor than ours. Yes, their guns were somewhat more powerful. But our soldiers were better trained, more motivated, willing to sacrifice themselves in ways American soldiers were not. Our engineers were more creative, more willing to find unconventional solutions to material limitations. This was what we told ourselves, and the evidence of our early victories seemed to confirm it. Then, in 1943, intelligence reports began arriving from the Pacific Islands describing a new American weapon. The reports were fragmentary, often from survivors of battles where most of our forces had been killed. A tube carried on the shoulder, they said. A rocket that destroys tanks with a single shot. We catalogued these reports in our files, but treated them with skepticism. Shoulder-fired rockets were not revolutionary. We had developed our own lunge mines, pole charges, shaped demolition devices. But an effective man-portable weapon that could reliably penetrate modern armor from significant range. The engineering challenges seemed insurmountable. High-explosive warheads worked through blast pressure and fragmentation. Against thin armor or unarmored vehicles, they were effective. The explosion would buckle plates, send fragments through openings, kill or wound the crew. But against thick, hardened armor, high explosives were nearly useless. The blast pressure would dissipate across the surface, following the path of least resistance around the obstacle rather than through it. This was basic thermodynamics, as fundamental as the fact that heat flows from hot to cold, or that pressure equalizes across connected spaces. You could not focus explosive force into a narrow, penetrating jet, energy dispersed. That was the law. To penetrate thick armor, you needed kinetic energy, a dense projectile traveling at high velocity. This required a powerful gun with a long barrel to accelerate the round and a heavy mount to absorb the recoil. A man could not carry such a weapon and remain mobile. Therefore, truly effective anti-tank capability required vehicles, tank destroyers, anti-tank guns on wheeled carriages, or tanks themselves. This conclusion was so obvious, so well established by years of testing and combat experience, that any claim to the contrary seemed impossible. The Americans were good at mass production. This we acknowledged freely. Their shipyards launched vessels faster than we could sink them. Their aircraft factories produced thousands of planes where we produced hundreds. Their assembly lines could equip entire armies with standardized weapons in timeframes that seemed almost supernatural to our resource-starved manufacturing base. But superior engineering, revolutionary innovation, these were German strengths, Japanese strengths. The Americans were mechanics and manufacturers. They copied proven designs, simplified them for mass production, and overwhelmed their enemies with quantity rather than quality. I had examined captured American weapons before. The M1 Garand rifle arrived in our laboratory in 1943, taken from a dead Marine on Guadalcanal. It was well manufactured, certainly. The semi-automatic operation gave American infantry a higher rate of fire than our bolt-action Type 38 Arisaka. But the Garand was also heavy 9.5 pounds unloaded and mechanically complex. It required precise manufacturing tolerances, careful maintenance, and regular cleaning. In the jungle environments of the Pacific, in the mud and rain and salt spray, complexity was a weakness. Our Arisaka was simpler, lighter, and more reliable under adverse conditions. Different design philosophies, different operational environments, neither clearly superior in all circumstances. This was how I rationalized every piece of American equipment I examined. They had resources, we had ingenuity. They had quantity, we had quality. They could afford to build complicated weapons because their factories had electric power and precision tooling and abundant steel. We had to be more clever, more efficient, more willing to accept calculated risks. The Zero fighter had no armor protection and limited ammunition, but it was light and maneuverable. The Sherman tank was heavier and better armored than our Type 97, but it was also taller and easier to spot. Every advantage came with corresponding disadvantages. Every weapon was a compromise. In February of 1945, as American forces advanced through the Philippines and prepared for the invasion of Okinawa, a damaged M1A1 Bazooka was recovered from a battlefield on Luzon. Some American soldier had been killed or forced to abandon his weapon during a firefight. Japanese infantry collected it from the mud, along with 2 intact M6A1 rockets, and shipped the whole assembly back to Tokyo through our increasingly disrupted supply lines. It arrived at our research facility on March 3, 1945. I remember the date precisely because it was my 29th birthday. I had requested an assignment to the Captured Weapons Analysis Team, specifically to examine this American anti-tank weapon that had reportedly been destroying our armor with such ease throughout the Pacific campaigns. I wanted to understand it, to measure its actual capabilities against the exaggerated claims in battlefield reports, to find its weaknesses so we could develop countermeasures or tactical responses. I expected to find a heavy, complicated device, something that required extensive training and perfect conditions to operate effectively, something that explained American success through mechanical advantage, but also revealed vulnerabilities we could exploit. What arrived in my laboratory was 54 inches of seamless steel tubing. The weapon lay on our examination table like an insult. The M1A1 Bazooka, named, we had learned, after some American comedian's novelty musical instrument, which seemed perfectly indicative of American culture's seriousness even in matters of war. Total weight, 13 pounds, 4 ounces. A boy could carry this weapon for miles without significant fatigue. Our Type 4 launcher, which it supposedly replaced in role and capability, weighed over 40 pounds without ammunition. The construction was almost offensive in its simplicity. A seamless steel tube, 54 inches long, 2.36 inches in diameter. An electrical firing mechanism powered by 2 ordinary flashlight batteries, the kind you could purchase in any hardware store. A basic shoulder rest made of wood and metal, simple iron sights, no complex optics, no elaborate recoil mechanisms, no heavy mounting systems, no sophisticated aiming devices. According to the American training manual we had captured, a soldier could be trained to use this weapon competently in less than 1 day. My first reaction, and I am ashamed of this now, but I must be honest about my thinking at the time was satisfaction. This crude tube seemed to confirm everything we had been told about American engineering philosophy. Where was the precision? Where was the sophistication? Where was the innovation? This looked like something assembled in a village workshop, not a weapons system that had supposedly revolutionized infantry anti-tank capability. The tube was welded, not machined. The components were stamped metal, mass-produced with minimal finishing. The entire device could probably be manufactured in under an hour by semi-skilled labor. "Examine the rocket," I instructed my assistant, Lieutenant Yamamoto, a young engineer who had joined our department 6 months earlier after graduating from Waseda University. "I want to understand what propellant they're using, what thrust characteristics, what accuracy they're achieving with such a simple design." We had recovered 2 intact M1A1 rockets along with the launcher. Each rocket measured 21 inches long and weighed 3.5 pounds. The rocket motor occupied the rear third of the projectile, a simple solid fuel design with nothing particularly innovative in its configuration. We cut one rocket open carefully in our munitions laboratory, taking extensive precautions because we didn't know if American explosive fillers had different stability characteristics than our own compounds. The propellant was standard, a mixture similar to what we used in our own rocket and mortar rounds. The burn rate looked consistent and predictable. The fins were stamped sheet metal, spot welded to the motor tube crude construction by our standards, but probably adequate for the short flight distances involved. Everything about the rocket motor suggested mass production techniques optimized for speed and cost, rather than precision or performance. Cheap, fast, thousands rolling off assembly lines daily to arm hundreds of thousands of soldiers. Typical American manufacturing philosophy. "Where is the armor-piercing penetrator?" Yamamoto asked, examining the warhead section with growing confusion. This was the question that had puzzled me from the moment I first saw the weapon. Anti-tank projectiles required dense metal cores, hardened steel or tungsten carbide, shaped to penetrate armor through kinetic force. The warhead of the M1A1 rocket was a conical shape approximately 5 inches long, filled with what appeared to be Composition B explosive, a 50-50 mixture of RDX and TNT. We knew this explosive compound well. It was powerful, certainly, with a detonation velocity around 8,000 meters per second. We used similar mixtures in our own demolition charges and aerial bombs. But the warhead casing was thin sheet metal and the nose cone was lined with copper. Copper, not steel, not tungsten, not any of the hard materials you would use for armor penetration. Copper is a soft metal, excellent for electrical conductivity and corrosion resistance, but useless for penetrating hardened steel. Why would the Americans line their anti-tank warhead with copper? "There is no penetrator," I said slowly, turning the sectioned warhead in my hands, examining the copper liner that formed the inner surface of the conical cavity. The warhead is a pure high explosive, with a copper liner forming a hollow cone. Yamamoto looked at me with the same confusion I felt. Then how does it penetrate armor? The explosive force would dissipate against the surface. Basic thermodynamics. The blast pressure would follow the path of least resistance, which is outward and around the armor plate, not through 6 inches of hardened steel. "I know," I interrupted, perhaps more sharply than I intended. I understood the physics as well as he did, probably better. I had spent 11 years studying and applying explosive chemistry and metallurgy. An explosion against thick armor plate would create tremendous pressure, certainly. It would create noise, flash, thermal effects. It might spoil the interior surface if the explosion was powerful enough and the armor was brittle, sending fragments of metal into the crew compartment. But actual penetration, creating a hole completely through 6 inches of solid, hardened steel plate with nothing but high explosive and a copper liner? Impossible. The fundamental laws of physics did not allow it. You could not compress and focus explosive force into a coherent, penetrating jet. Energy dispersed according to entropy. Explosions were omnidirectional events. The chemical reaction released gas at high pressure, and that gas expanded in all directions simultaneously, following paths of least resistance. Against a solid steel obstacle, the expanding gases would flow around the obstacle, not through it. This was as fundamental as gravity or thermodynamics. You might as well claim you could make water flow uphill by adding more water. Perhaps the battlefield reports were exaggerated, Yamamoto offered, and I could hear in his voice that he wanted to believe this, needed to believe this. Battlefield observations are notoriously unreliable. Panicked soldiers see a tank destroyed and assume the American weapon was responsible, when actually the tank was struck by conventional artillery or mines. Or perhaps the American weapons are only effective against thin armor, and the reports of penetrating heavy armor are propaganda. I desperately wanted to believe this explanation. The alternative was that I had fundamentally misunderstood something about explosives and materials, science fields I had studied for more than a decade, fields where I had published research papers and designed weapons that actually worked. If this crude American tube could actually penetrate thick armor with nothing but explosive force, then every assumption underlying our anti-tank doctrine was wrong. We need to conduct a live-fire test, I said, against actual armor plate under controlled conditions. We scheduled the test for March 6th, 3 days later, at the Sagami Proving Grounds. We would fire the captured bazooka at our decommissioned Type 97 Chiha tank and at the prepared test plates of increasing thickness. If the weapon performed as reported, we needed to understand its actual penetration capabilities and limitations. If it failed to penetrate, we could file a report explaining that American claims were exaggerated and our armor remained effective. I spent those 3 days reviewing everything I knew about explosive physics, searching for some theoretical framework that might explain penetration without kinetic energy. There was something called the Monroe effect, discovered by an American chemist named Charles Monroe back in 1888. He had observed that explosive charges with hollowed cavities created slightly focused jets that could cut into metal surfaces more effectively than flat explosive charges. The effect was measurable but modest, perhaps 30 to 40% improvement in penetration against thin plates. The Monroe effect was a curiosity, a footnote in explosive physics textbooks. It was sometimes used in demolition work against concrete or rock, where the improved penetration allowed for more efficient braking. But for anti-armor warfare, against a hardened steel plate several inches thick, the effect was far too weak to be militarily significant. Every textbook, every researcher who had studied shaped charges concluded that the penetration improvement was marginal at best. But what if I was wrong? What if there was something in the geometry, in the liner material, in the explosive chemistry, that created effects far beyond what the basic Monroe effect predicted? What if the Americans had discovered something that our theoretical physics had missed? I pushed these thoughts away. I was catastrophizing, letting battlefield rumors override solid engineering principles and experimental evidence built up over decades by researchers in multiple countries. Tomorrow's test will provide clarity. We would fire the American rocket at our tank. The warhead would detonate with impressive noise and flame. It would perhaps damage or crack the armor surface, and we would write a report explaining that the weapon's effectiveness had been vastly overstated by combat observers who mistook correlation for causation. The night before the test, I could not sleep. I lay in my small apartment in Tokyo, listening to the distant sounds of the city preparing for air raids that had become routine since the American B-29 bombers began their systematic destruction of Japanese urban areas. I thought about copper liners and explosive collapse patterns, and the growing certainty in my mind that tomorrow would change something fundamental in my understanding of the world. I was correct, but I had vastly underestimated how complete that change would be. The morning of March 6, 1945, was clear and cold, good weather for outdoor testing. We departed Tokyo by military truck at 0600 hours. driving southwest through countryside that showed increasing signs of war strain. Farmland that should have been planted with rice stood empty because there were no young men to work it, no fertilizer to enrich it, no fuel for the equipment to till it. We passed through villages where every third house stood empty, the occupants either conscripted or evacuated or dead. We arrived at Sagami in 0800 hours. The proving ground occupied a wide valley surrounded by low forested hills, with earthen berms for absorbing explosions and catching stray projectiles. The facility had once been busy with constant testing of new weapons and ammunition, but by March of 1945, most of our weapons development had ceased. We lacked the materials, the time, and increasingly the hope that new weapons would change the trajectory of the war. The Type 97 Chi-Ha tank sat in the firing zone where our preparation team had positioned it the previous day. It was positioned at a 45-degree angle to give us clear observation of both frontal and side armor. This particular tank had been damaged in China in 1942. The engine was destroyed, the tracks partially removed, but the armor hull remained intact. Frontal armor, 25 mm, roughly 1 inch. Maximum armor thickness on the gun mantlet, 33 mm. This was admittedly thin by current standards. American Sherman tanks had frontal armor nearly twice as thick, but it was representative of what we had, and it would serve for initial testing. The test plates stood on wooden frames next to the tank, 50 mm, 75 mm, 100 mm, 125 mm, and 150 mm, 2 inches, 3 inches, 4 inches, 5 inches, 6 inches of hardened steel plate. If this American weapon actually functioned as the reports claimed, these plates would tell us its penetration limits. If it failed, we would know that 6 inches of armor, which was thicker than any production tank in the world carried, provided adequate protection. Our test team numbered 6 personnel. Myself, Lieutenant Yamamoto, 2 ordnance technicians named Sato and Nakamura, a photographer named Fujita to document the results with still images, and a demolitions expert, Sergeant Ishii, who would actually operate the captured bazooka. Ishii had spent 2 days studying the American training manual. We had obtained a mimeographed field guide that explained the weapon's operation in straightforward, almost simplistic language. Even the manual's presentation bothered me. Americans wrote technical documentation as if training children, breaking every procedure into numbered steps with simple diagrams. It was effective for rapid training of conscripts, certainly, but it reflected a military philosophy built on the assumption that weapons should be operable by soldiers of average intelligence with minimal preparation. Our philosophy was different. We expected soldiers to master their weapons through extended training, to understand the principles underlying operation, to develop almost spiritual connection with their equipment. The American approach seemed mechanical, impersonal, focused purely on functional outcomes without any deeper understanding. Yet this approach allowed them to train millions of soldiers quickly, while our more rigorous methods limited the speed at which we could replace casualties. The manual specifies an effective range of 100 yards against moving armor, up to 300 yards against stationary targets, Ishii reported, reading from the translated document. Penetration is listed as... He paused, double-checking his translation of the English technical specifications. 5 inches of homogeneous armor plate at 0 degrees obliquity. 5 inches, 127 millimeters, more than 4 times the thickness of our Chi-Ha's frontal armor. Nearly double the frontal armor of a Sherman tank. American propaganda, Yamamoto muttered, loud enough for everyone to hear. They always exaggerate their capabilities. Look at their claims about bombing accuracy. They say they can hit specific factories from 6 miles up, but half their bombs land in empty fields. Several technicians laughed, and I understood why. We needed to believe this was an exaggeration. The alternative was too disturbing. We positioned ourselves at 100 meters distance, close enough to ensure accuracy with this unfamiliar weapon system, far enough to observe the full effect with reasonable safety. Ishii loaded the M1A1 rocket, a procedure that required simply sliding it into the front of the tube until it's seated against the electrical contact. No complex loading mechanism, no careful alignment, just insert and fire. The rocket protruded from the front of the tube, held in place by its fins resting against the tube's interior. The weapon looked absurd. A simple pipe resting on a man's shoulder, pointed at a 14-ton armoured vehicle. David with a sling facing Goliath. Except this, David's sling was made by American factory workers in some assembly plant in Pennsylvania or Ohio, stamped out by the thousands per day. I watched through binoculars from behind our concrete observation barrier. My hands were steady, my breathing calm. I felt no particular anxiety. I expected a loud explosion, some damage to the tank's surface, and confirmation that physics worked the way I understood it to work. "Ready to fire," Ishii called out, his voice carrying across the proving ground. "Fire when ready," I responded. The launch was almost anticlimactic. A sharp crack as the electrical system ignited the rocket motor, a burst of flame and smoke from the rear of the tube, and the rocket streaked across the 100 meters faster than I could track it with my binoculars. Perhaps half a second of flight time, then impact. What happened next? I have replayed in my mind countless times over the past 60 years. The sound arrived first, not the dull boom of a normal explosion, but a sharp, violent crack, like the sky itself being torn open. The tank shuddered from the impact. A brilliant flash of white light erupted from the point where the rocket struck the frontal armor, approximately where the driver's position would be if this tank were occupied. Then, impossibly, smoke and flame jetted from every opening in the tank, the driver's vision port, the hull machine gun aperture, the open turret hatch in the rear. The explosion itself lasted perhaps half a second. When the smoke cleared enough to see, there was a hole, a perfect circle, approximately 3 inches in diameter, cut through 1 inch of hardened steel plate as cleanly as a punch through paper. The edges of the hole glowed red-hot, the metal still semi-molten, dripping like wax. Around the penetration, the armor plate showed no buckling, no cracking, no deformation, just a clean, impossible hole burned straight through. Someone made a sound, a gasp, or a curse. I realized seconds later that it was me. We approached the tank slowly, waiting for the superheated metal to cool enough that we could examine it safely without risk of burns. No one spoke. Sato, one of our ordnance technicians, kept making an unconscious gesture, touching his forehead, his chest, his shoulders, as if warding off evil spirits. Fujita, the photographer, circled the tank, taking pictures from multiple angles, his camera clicking like an insect's wings. When I could finally touch the armor around the penetration, I felt the edges. They were smooth, almost glass-like, where the steel had melted and resolidified. The hole went completely through the frontal plate. I could see daylight on the other side. Inside the tank, we found catastrophic damage. The jet had continued through the internal structure, melting through the driver's seat frame, punching through the engine firewall, shredding components throughout the crew compartment. If this tank had been occupied, the crew would have died instantly, not from blast pressure or fragmentation, but from a jet of molten copper and steel traveling at speeds that seemed impossible. "Test the thicker plates," I heard myself say. My voice sounded distant, mechanical, as if someone else were speaking through my mouth. We set up the 50mm plate, 2 inches of hardened steel, thick enough to stop any rifle caliber round, thick enough to resist most artillery fragments. Ishii reloaded the bazooka with last intact rocket. The procedure took perhaps 30 seconds. Simple, fast, no complex loading drill required. Fire, the same tearing crack, the same impossible result. The shaped charge jet punched completely through 2 inches of solid steel, leaving that same perfectly circular hole with melted edges. We had no more rockets to test, but I didn't need more tests. I had seen enough to understand that something fundamental had changed, that some principle I thought was impossible was actually trivially achievable, and that every assumption underlying anti-tank warfare had been rendered obsolete by a weapon so simple that a farm boy from Iowa could be trained to use it in one afternoon. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Back in Tokyo, I spent the next 5 days in our laboratory doing nothing but studying the physics of shaped charges. I pulled every research paper we had on the Monroe effect, every document on explosive physics, every captured German technical manual that might contain information. I built mathematical models, calculated pressures and velocities, and tried to understand how we had missed something so fundamental. The principle, once I forced myself to accept what I had witnessed, was elegant in its simplicity. The shaped charge, that was what the Americans called it, and the Germans had their own version called the Hohlladung. The conical cavity in the warhead, lined with copper, created a phenomenon that transformed the Monroe effect from a curiosity into a revolution. When the explosive detonated, the detonation wave traveled through the explosive material at approximately 8,000 meters per second. This wave collapsed the copper liner inward from the base of the cone toward the apex, like folding an umbrella but at hypersonic speeds. The collapsing liner did not simply crumple, it formed a jet, a narrow stream of copper that was neither fully solid nor fully liquid, but existed in a superplastic state that behaved according to fluid dynamics rather than solid mechanics. This jet achieved velocities exceeding 20,000 meters per second, more than 50 times the speed of sound, faster than any rifle bullet ever fired, faster than any kinetic penetrator launched from any gun. The jet carried tremendous kinetic energy, not from the velocity of the warhead itself, which was traveling at perhaps 300 meters per second when it struck, but from the internal velocity created by the explosive collapse. The pressures involved were incomprehensible to normal engineering experience, millions of pounds per square inch, temperatures exceeding 5,000 degrees Celsius. At these extremes, hardened steel ceased to behave like solid matter. It behaved like water. The copper jet flowed through the armor plate using hydrodynamic penetration, both the jet and the armor acting as fluids under these impossible pressures. This was why the velocity of the warhead itself did not matter. A shaped charge fired from a recoilless rifle, dropped from an aircraft, or launched from a simple rocket motor produced the same jet velocity, the same penetration. The energy came from the explosive, released at the moment of detonation, not from kinetic energy built up during flight. This meant a soldier on foot could carry a weapon that generated more penetrating power than a tank's main gun. The genius of the design was its independence from traditional limitations. You did not need a heavy gun. You did not need a powerful propellant charge. You did not need precise aim at long ranges, because the warhead would work at any angle within reasonable limits. You just needed a way to deliver the warhead to the target. A simple rocket motor was sufficient, and the physics of explosive collapse would do the rest. I calculated the penetration potential of the M1A1 rocket warhead based on the copper liner dimensions and the explosive charge weight. The theoretical maximum was approximately 150 millimeters, nearly 6 inches of homogeneous steel armor. Our test had stopped at 2 inches only because we had run out of rockets. But the mathematics indicated that this simple warhead, this crude device assembled by semi-skilled workers and costing perhaps $20 American to manufacture, could penetrate armor thicker than any production tank in the world carried. The tactical implications were staggering. Every tank we had built, every tank we would ever build, was vulnerable to a weapon that could be carried by infantry. Our armor doctrine, the entire theory of armored warfare that had guided military thinking for 25 years, had been built on the assumption that armor protection could be made thick enough to resist infantry weapons. Heavy machine guns, anti-tank rifles, even light artillery could be defeated by sufficient thickness of hardened steel. But shaped charges changed everything. You could not build armor thick enough to stop them without making tanks immobile. 6 inches of steel armor would weigh so much that no engine we could manufacture would move the vehicle at useful speeds. And even 6 inches might not be enough. The Germans were already developing larger shaped charges, and the physics allowed for scaling to bigger diameters and greater penetration. We had reached the end of an evolutionary pathway. The balance between armor and anti-armor that had driven tank development since 1917 had been shattered by a principle so simple that I felt physically ill every time I thought about it. But what haunted me more than the tactical implications was the timeline. I pulled every intelligence report we had received about the bazooka. The weapon had been deployed in November of 1942, more than 2 years earlier. First combat use was in North Africa against German and Italian armor. By 1943, American infantry units were training with bazookas as standard equipment. By 1944, improved versions with larger warheads were in mass production. The Americans had understood shaped charge physics years before we did. They had weaponized it, tested it, manufactured it by the hundreds of thousands, and distributed it to their infantry, while we were still developing anti-tank rifles based on 19th century kinetic penetration principles. How had we missed this? How had our intelligence services, our weapons researchers, our entire technical establishment failed to recognize the revolutionary nature of this weapon? The answer, as I reviewed our files, made me ashamed. We had received the intelligence. Captured bazookas had been sent to research facilities in Japan as early as 1943. Reports had been filed describing the weapon's effects. Photographs showed the characteristic circular penetrations. Some of those reports sat in filing cabinets in the very building where I worked, but no one believed them. The penetration values seemed impossible, so they were dismissed as battlefield exaggeration or measurement error. The principle seemed to violate established physics, so it was assumed the Americans were lying or that observers were misinterpreting what they saw. When one research team actually tested a captured bazooka warhead against thin plate and observed significant penetration, their report was filed away because it contradicted doctrine, and no one wanted to be the engineer who told the army that all our anti-tank weapons were obsolete. We had seen what we expected to see. We had believed what we wanted to believe, and in doing so, we had sent our soldiers into battle against a weapon they had no defense against, no understanding of, and no effective counter to. I drafted my report over 3 days in mid-March of 1945. It was the most difficult document I have ever written. I had to explain to officers who knew nothing about explosive physics why everything they understood about armor warfare was wrong. I had to present evidence that would force them to acknowledge we had been fighting with obsolete weapons and obsolete thinking, while the Americans had leapfrogged an entire generation of technology. The report was 15 pages of technical analysis, calculations, and recommendations. The core conclusions were simple. Shaped charge weapons represented a fundamental revolution in anti-tank capability. Every American infantry squad now carried weapons that could destroy any Japanese tank with a single shot. Our tanks, our tank destroyers, our entire armored force was vulnerable to simple tube-launched rockets that weighed less than 4 pounds. I recommended immediate development of our own shaped charge weapons, but I also had to include the bitter reality. We lacked the copper for mass production of liner elements. We lacked the high-quality explosives for optimal performance, and we were at least 3 years behind in understanding physics and engineering. By the time we could field an effective shaped charge weapon in meaningful numbers, the war would be over. My final recommendation was the hardest to write. Our anti-tank doctrine should shift focus away from vehicle versus vehicle combat and toward obstacles, mines, and prepared defensive positions. Our tanks should be preserved for infantry support rather than tank versus tank battles, because in any engagement against American armor, we would face not just their tanks but their infantry armed with weapons that made armor thickness almost irrelevant. The Americans were not the only ones who had developed shaped charges, I learned. The Germans had their own versions, the Panzerfaust, the Panzerschreck. Intelligence reports from Europe described German infantry destroying Soviet tanks at ranges where the Soviets could not effectively return fire. The Panzerfaust was even simpler than the bazooka, a disposable tube with a shaped charge warhead, fired once and discarded. German factories were producing them by the hundreds of thousands. Every major combatant except Japan had recognized the potential of shaped charges and developed effective weapons. We were alone in our obsolescence, alone in our continued reliance on kinetic penetrators and contact charges. Why had we fallen so far behind? I spent many sleepless nights considering this question. Part of the answer was resources. We lacked the copper, the manufacturing capacity, the testing facilities to develop and produce complex weapons at scale. But the deeper answer was cultural and intellectual. We had convinced ourselves that Japanese engineering was inherently superior, that our limitations in raw materials could be overcome through innovation and creativity. We had internalized propaganda about spiritual strength compensating for material weakness, and most critically, we had rejected evidence that contradicted our assumptions because accepting that evidence would require acknowledging that we were losing not just battles, but the underlying technological competition. The Germans had no such illusions. They knew they were fighting enemies with greater industrial capacity, so they focused on weapons that provided tactical advantages: better tanks, better anti-tank weapons, better infantry equipment. They still lost because they were outnumbered and surrounded, but they fought with weapons that reflected realistic assessment of the battlefield. Japan had fought with weapons that reflected what we wished were true rather than what was actually true, and the difference cost us everything. In early April of 1945, I began examining other captured American equipment with new eyes, looking for patterns I had missed because of my assumptions about American engineering. The M4 Sherman tank, which our propaganda had mocked as a Ronson lighter because it supposedly caught fire easily, turned out to be a remarkably sophisticated design. Yes, early versions had gasoline engines and ammunition storage that made them vulnerable to fires. But by 1944, the Americans had addressed these issues with wet storage, different ammunition arrangements, and diesel engines in later variants. What I had dismissed as crude engineering was actually optimization for mass production and battlefield repair. The Sherman's vertical armor made it easier to manufacture than sloped armor. Its radial engine was powerful and reliable. Its transmission was simple but effective. Most critically, it had a gyro-stabilized gun, a system that allowed accurate firing while moving. Our Type 97 could not fire accurately on the move. We had to stop, aim carefully, and fire. The Sherman could engage targets while maneuvering, giving American tank crews a decisive advantage in the fluid combat of armored warfare. This was not crude engineering. This was sophisticated engineering applied to the actual problems of combat rather than to abstract ideals of perfection. The Sherman also had a radio in every vehicle. Every single tank could communicate with every other tank and with supporting infantry and artillery. Our tanks rarely had radios, only command tanks in each platoon. This meant American armor fought as coordinated teams, while our tanks fought as individuals, each commander able to see only what was in his immediate vicinity. I obtained production statistics through intelligence channels, though I suspected the numbers were too large to be accurate. American factories had produced 49,000 Sherman tanks by the end of 1944. 49,000. We had produced approximately 6,000 tanks of all types in our entire history as a nation. For every Japanese tank, there were 8 American tanks, and the American tanks were better armed, better armored, more reliable, and supported by better logistics. The M1 Garand rifle that I had dismissed as overcomplicated. American factories produced more than 5 million of them. An entire army, multiple armies equipped with semi-automatic rifles that gave every infantryman the sustained firepower of a light machine gun. Our soldiers carried bolt-action rifles, most of them designed in 1905. Not because bolt-actions were superior, but because we could not manufacture semi-automatic rifles at the scale required to equip millions of soldiers. The pattern became impossible to ignore. Every piece of American equipment reflected the same philosophy: good enough to be effective, simple enough to mass produce, designed for soldiers of average training and ability. The Americans did not build perfect weapons. They built adequate weapons in overwhelming quantities, supported by logistics that ensured those weapons always had ammunition, fuel, spare parts, and trained operators. We had built excellent weapons in pathetically small quantities, supported by logistics that collapsed under any sustained combat, operated by soldiers who were expected to compensate for material shortages through spiritual strength and tactical flexibility. Which philosophy has proven correct? The evidence was devastating. American forces were now within 300 miles of the Japanese home islands. Our navy was destroyed, our air force reduced to kamikaze attacks because we lacked the fuel and trained pilots for conventional operations, our army scattered across China and the Pacific Islands with no way to reinforce or resupply them. In April of 1945, I was summoned to a meeting with senior Imperial Army officers. They wanted my assessment of anti-armor defenses for the home islands. American invasion was expected by summer or fall of 1945. They needed recommendations for stopping American tanks when they landed on Japanese beaches. I stood before 6 generals and 3 admirals, men with decades of service, uniforms covered in medals and decorations, and I told them the truth that no one wanted to hear. "We cannot stop their tanks," I said, and the room went silent. Every American infantry squad carries weapons that can destroy our armor with a single shot. They have shaped charge technology years ahead of ours. Even if we could build tanks with armor thick enough to resist bazookas, which we cannot, because we lack the steel and the engines to move such vehicles, we still face a fundamental asymmetry. I showed them the calculations. An American bazooka cost approximately $20 to manufacture and weighed 13 pounds. A Japanese tank cost hundreds of thousands of yen to build and required months of production time with materials we no longer had reliable access to. The mathematics of attrition was brutal. They could afford to expend 10 rockets to destroy 1 tank and still come out ahead. Our anti-tank defenses should focus on obstacles, mines, and prepared positions, I continued. Tank traps, artificial terrain that channels their armor into killing zones where our artillery can engage them, anti-tank guns positioned in concealed positions with overlapping fields of fire, infantry equipped with whatever shaped charge weapons we can manufacture, concentrated for close-range ambushes. General Anami Korichika, the Vice Minister of War, leaned forward. His expression was difficult to read, anger perhaps, or resignation. "Are you saying our armor is useless?" he asked quietly. "I am saying our armor is outmatched, sir. Not by American tanks primarily, but by American infantry. A weapon that costs them $20 can destroy a tank that costs us hundreds of thousands of yen and requires months of production time. If we commit our armor to tank versus tank battles, we will lose not because our tanks are inferior, though they are, but because every American soldier is a potential tank killer." Another general spoke up. "Then we develop our own shaped charges. We copy their design, manufacture them in quantity, and equip our infantry." "We are already attempting this, sir," I confirmed, "but we face severe constraints. Copper for the liner elements is critically scarce. We have redirected some copper from electrical applications, but it is not enough for mass production. High-quality explosives are also in short supply. Most critically, we are approximately 3 years behind in understanding physics and engineering optimization." I paused, choosing my next words carefully. Everyone in this room knew the war situation was desperate, but stating it explicitly was dangerous. By the time we can field effective shaped charge weapons in meaningful numbers, the strategic situation will have. I searched for a euphemism that would be understood without being treasonous, evolved beyond the point where such weapons can alter the outcome. The room was silent. No one wanted to say what everyone was thinking. By the time they developed adequate weapons, the war would be over. "How long have the Americans had these weapons?" one of the admirals asked. "Combat deployment began in November of 1942, sir, in North Africa. And we are learning about them now, in April of 1945? We received intelligence reports as early as 1943, sir. Captured specimens were sent to research facilities. Reports were filed. I hesitated, then decided I owed these men the complete truth. Those reports were not given sufficient priority because the claimed performance seemed impossible. The penetration values contradicted established doctrine. It was assumed the reports were exaggerated or inaccurate. Another long silence. Finally, General Anami spoke. "Your report is noted, Engineer Tanaka. Your recommendations will be considered. You are dismissed." I bowed deeply and left the room. As I walked through the corridors of the War Ministry building, I passed portraits of heroes from previous wars, the Russo-Japanese War, the First Sino-Japanese War. Victories built on superior tactics, superior morale, superior will. I wondered if any of those heroes had ever experienced what I had just experienced. The moment when you realize that courage and tactical brilliance and spiritual strength mean nothing against an enemy who has better weapons, more weapons, and the industrial capacity to replace losses faster than you can inflict them. The bazooka had taught me that modern wars are not won by the best soldiers. They are won by the best logistics, the best factories, and the best supply chains. They are won by economies that can produce millions of weapons instead of thousands, by nations that can train replacements faster than casualties accumulate, and by industrial bases that can absorb catastrophic losses and continue producing at scales that seem impossible. Japan had never had a chance, not after Pearl Harbor, perhaps not even before. We had attacked an industrial superpower that we fundamentally misunderstood, and that superpower had crushed us not through superior courage or better soldiers, but through superior manufacturing, superior logistics, and weapons that were good enough, produced in quantities that were overwhelming. The shaped charge was just one example, but it encapsulated the entire pattern. While we had convinced ourselves that our weapons were adequate and our soldiers superior, the Americans had been revolutionizing infantry anti-tank warfare. While we had rejected evidence that contradicted our assumptions, they had been testing impossible ideas and accepting the results. While we had built a military based on what we wished were true, they had built a military based on industrial capacity and technological pragmatism. In May of 1945, American bombers destroyed most of our remaining research facilities in Tokyo. My laboratory was damaged but not destroyed. Many of my colleagues were killed. We continued working, but resources became increasingly scarce. Electricity was available only a few hours per day. Paper for reports was rationed. Test ammunition was almost impossible to obtain. We did develop a prototype-shaped charge warhead. It was crude, inefficient, far inferior to the American design. We lacked the precision manufacturing to create optimal liner geometry. We lacked sufficient copper, so we tried iron liners, which reduced penetration by nearly 40%. We lacked high-quality explosives, so we used whatever compounds we could obtain, which produced inconsistent results. Even if we had perfected the design, we lacked the capacity to produce them in meaningful quantities. American factories were producing thousands of bazooka rockets per day. We might have managed a few hundred per month if we had diverted resources from other critical needs. The war ended in August of 1945. I heard the Emperor's voice on the radio, announcing the acceptance of the Potsdam Declaration, calling for the endurance of the unendurable. I felt relief more than anything else. The killing would stop. The cities would stop burning. Japan would survive, even if the empire would not. During the American occupation, I was retained as a technical consultant. The Americans wanted Japanese engineers to help with reconstruction, to document what we had been working on, to transition military facilities to civilian purposes. It was strange at first, working with the enemy. But the American engineers I met were not so different from myself, technically trained men trying to solve problems, curious about the world, interested in how things worked. One of them, a captain named Morrison from somewhere in Pennsylvania, visited our partially rebuilt laboratory in October of 1945 to inventory captured Japanese weapons and review our research documentation. He was perhaps 30 years old, friendly in the casual way Americans were friendly, treating me as a colleague rather than as a defeated enemy. When he saw the bazooka test results still hanging on our wall, the photographs of the penetrated armor plates, the mathematical calculations of jet formation and velocity, the detailed analysis I had written, he laughed. Not mockingly, but with genuine amusement. "That weapon scared the hell out of us when we first tested it," he said in English. I had been studying English during the occupation, reading technical manuals and conversing with American personnel. Nobody believed it would actually work. The shaped charge effect was purely theoretical, you know. Some Swiss physicist, I think his name was Neumann, published a paper about it in the 1930s. One of our ordnance guys at Aberdeen Proving Ground read it and thought, "Hey, maybe we can make a tank killer out of this." And everyone else told him he was crazy. I said quietly, understanding the pattern. "Exactly. You can't focus explosive force like that," they said. "Physics doesn't work like that." The penetration values he was predicting seemed impossible, but he ran the tests anyway, and it turned out the crazy idea was right. Sometimes the stuff that sounds impossible is just stuff nobody's tried yet. I thought about this conversation many times over the following years. The cultural difference it revealed was profound. The American engineer had seen a theoretical prediction that contradicted conventional wisdom, and his response was to test it. Our engineers, myself included, had seen test results that contradicted conventional wisdom, and our response was to assume the tests were flawed. Both approaches were scientifically defensible. Extraordinary claims require extraordinary evidence. Skepticism is appropriate when confronted with results that seem impossible, but there is a difference between healthy skepticism and defensive rejection. The Americans had been skeptical but willing to test. We had been skeptical and unwilling to believe. "We had reports about your weapon as early as 1943, I told Morrison. Captured bazookas, penetration tests, documented effects. But the reports were not believed. The performance seemed too good to be true, so it was assumed to be propaganda or error." Morrison nodded slowly. "That must have been." He searched for the right word. "Frustrating, to realize you had the information but didn't act on it." "Frustrating," I agreed, though the word was far too mild for what I felt. We convinced ourselves that American engineering was crude, that quantity could not substitute for quality, that our material limitations could be overcome through innovation and spirit. The bazooka proved all of those assumptions wrong. "I don't know if I'd say our engineering was better," Morrison said thoughtfully. "Different philosophy, maybe. We designed stuff to work well enough, to be easy to manufacture, to be operated by average soldiers with minimal training. Your Type 38 rifle is actually more accurate than our Garand at long range. Your long-lance torpedo was better than anything we had. But we built millions of Garands, and you built maybe 1,000,000 Type 38 seconds, so in the end," he shrugged. "Quantity has a quality all its own, I guess." This was perhaps the most honest assessment of the war I had heard from anyone on either side. Not that one side was inherently superior, but that different circumstances called for different approaches, and the side with greater industrial capacity could afford to optimize for mass production rather than perfection. I remained in weapons research until 1950, then transitioned to civilian manufacturing. The occupation was ending, Japan was beginning its long recovery, and there was immense need for engineers who understood materials science and production systems. I went to work for a company that would later become part of Toyota, designing improved steel alloys for automotive applications. Japan rebuilt. The cities rose from ashes. The economy recovered faster than anyone had predicted. We became America's ally, trading partner, and eventually economic competitor. The students I taught at Tokyo University went on to design some of the world's best automobiles, electronics, and industrial equipment. Japanese engineering regained its reputation for excellence. But I never forgot the bazooka. I kept one photograph from the March 6th tests, the Type 97 Chi-Ha tank, with that perfect circular hole burned through its frontal armor. I mounted it in a simple frame and kept it on my desk for 43 years, through career changes, through marriage, through my children's childhood. When my son Kenji was 12 years old, in 1963, he asked me what the photograph showed. We were in my study at home, and he had been looking at the various mementos and awards on the walls while I worked on technical drawings. "That is a hole in the armor plate," I told him, "made by an American weapon during the war." "How thick was the armor?" he asked, curious in the way children are curious about military equipment and weapons. 25 millimeters, about 1 inch. "That's thick," he said, impressed. "What kind of gun made that hole?" "Not a gun," I said. "A small rocket fired from a tube a soldier could carry on his shoulder. The rocket weighed less than 4 pounds. The entire weapon weighed 13 pounds. He looked at the photograph more carefully, then back at me. How could such a small weapon make such a clean hole through that much steel? I considered my answer carefully. I could give him the technical explanation: shaped charges, copper liners, hydrodynamic penetration. But he was 12 years old. The technical details mattered less than the lesson. It worked because the Americans were willing to believe in something that seemed impossible, I said. And we were not. That photograph reminds me that being wrong can teach you more than being right, if you are willing to learn from it. He nodded, not fully understanding, but he remembered the conversation. Years later, when he was an engineer himself working on hybrid engine technology, he told me that he had thought about that photograph many times, about the importance of testing ideas that seem impossible, about the danger of assuming you already know what will and will not work. The shaped charge principle that shattered my certainties in March of 1945 became the foundation of modern anti-tank warfare. The technology spread to every military in the world. The Soviet Union developed the RPG-7, which became the most widely used shaped charge weapon in history. America developed the TOW missile, the Hellfire, the Javelin, each generation more sophisticated, more accurate, more devastating. Modern tank designers build reactive armor, composite armor, cages and screens and slat armor, all trying to disrupt the shaped charge jets. It is an endless arms race, technology versus counter-technology, and it traces directly back to that simple bazooka that proved everyone wrong about what was possible. But the lesson I learned was not primarily about weapons technology. It was about intellectual humility, about the catastrophic consequences of believing your enemies are inferior because you need them to be, about the danger of rejecting evidence because it contradicts what you want to believe. Japan lost the Second World War for many reasons. We overextended ourselves, attacking too many enemies simultaneously. We lacked critical resources, oil, steel, rubber, and could not sustain long-term industrial war. We made strategic blunders, tactical errors, intelligence failures, but we also lost because we believed our own propaganda. We convinced ourselves that American soldiers were soft, that American weapons were crude, that American industry was quantity over quality. We needed to believe these things because the alternative that we had attacked an enemy vastly superior in industrial capacity, technological innovation, and material resources was too terrifying to contemplate. So we found evidence that supported what we wanted to believe, and we rejected evidence that contradicted our assumptions. The bazooka showed me the cost of that self-deception. A 13-pound tube, a copper liner shaped into a cone, and physics we had dismissed as impossible. A weapon so simple that a farm boy from Kansas could learn to use it in an afternoon, and so devastating that it rendered decades of armor development obsolete. It was elegant, it was efficient, it was exactly what you would design if you understood the problem clearly and had the freedom to question every assumption. The Americans did not defeat us because they were better people, or because they had superior culture, or because God favored them. They defeated us because they were willing to test crazy ideas, because they built weapons that were good enough in overwhelming quantities, because their factories could replace losses faster than we could inflict them, and because they accepted evidence even when it contradicted established doctrine. I am 89 years old now, writing this in 2005. The bazooka that changed my understanding of the world was replaced long ago by more sophisticated weapons. But every time I hear about some new technology that people say is impossible, some innovation that contradicts established theory, some approach that seems too simple to work, I remember March 6, 1945. I remember the sound of that shaped charge jet tearing through steel with a crack like reality breaking. I remember the impossible hole with its melted edges. I remember standing in my laboratory afterward, staring at test data that proved I had been wrong about something fundamental. I remember the sick feeling of understanding that we had sent soldiers and tank crews into battle against a weapon they had no defense against, because we had been too proud and too frightened to believe what the evidence showed us. That is the true legacy of the bazooka, for me. Not the tactical revolution in anti-tank warfare, though that was significant. Not even the demonstration of American industrial and technological capability, though that was important. The real legacy is the lesson about intellectual honesty and the courage required to accept being wrong. Your enemy's crude weapon might be revolutionary. Your superior engineering might be obsolete. The performance that seems too good to be true might actually be accurate. And the most dangerous assumption you can make in engineering, in war, or in life, is that you already understand everything, and that evidence contradicting your understanding must be flawed. I learned that lesson in the worst possible way too late to change outcomes, too late to save lives, too late to matter to the war, but I taught it to every engineering student I mentored over the following 40 years. Question your assumptions before reality forces you to. Test the ideas that sound impossible. Accept results even when they terrify you or contradict what you thought you knew. That is how you avoid building strategies on illusions. That is how you avoid sending people to die for assumptions that were never tested. The young engineers I taught are now senior researchers and executives themselves, leading companies and research institutes. Japan's economy recovered and prospered. We became known again for engineering excellence, for attention to detail, for manufacturing quality. But the best of those engineers, the ones who went furthest and accomplished the most, were the ones who learned that lesson about intellectual humility. They learned to question doctrine. They learned to test assumptions. They learned that the most important words in engineering are not, "that is impossible," but rather, "let us test it and see." That approach, that willingness to believe in possibilities that contradict what you think you know, is what separates merely good engineers from great ones. It is also what separates nations that adapt and survive from nations that cling to comfortable illusions until reality destroys them. I think about the young man I was in March of 1945, standing at a proving ground holding an American weapon I did not understand, convinced that my education and expertise meant I knew what was possible and what was not. I think about how completely wrong I was, and how much that wrongness cost in lives and suffering and national catastrophe. I cannot change what happened. I cannot bring back the tank crews who died facing weapons they had no defense against, or the soldiers who fought with inadequate equipment, or the civilians who suffered because their nation's leaders refused to accept evidence that contradicted their ideology. but I can ensure that the lesson is not forgotten. The bazooka taught me that impossible things become possible when someone is willing to question everything. It taught me that crude-looking solutions can be revolutionary. It taught me that your enemy might understand something fundamental that you have missed. And it taught me that the worst lies are the ones you tell yourself because you need them to be true. Those lessons are worth remembering, worth teaching, worth passing on to future generations. Not just for engineers and weapons designers, but for anyone who makes decisions based on assumptions about reality. Test your assumptions. Accept evidence even when it contradicts what you believe. Remain humble about the limits of your knowledge. That is how you avoid repeating history's mistakes. That is how you build a future on truth rather than illusion. The photograph still sits on my desk, though I am too old now to work regularly. The hole in that armor plate remains as perfect and impossible as it was 60 years ago, a permanent reminder that reality does not care what you believe, and that the universe will teach you what is possible whether you are ready to learn or not. I was not ready, but I learned anyway, and I have spent the rest of my life trying to ensure that others learn those lessons before reality forces them to, the way it forced me. That is the best I can do. That is the only redemption available to someone who learned the truth too late. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.